Thank you. Thank you for the kind introduction. And also I want to introduce Jiaping Zheng, and he's sitting down there. So Jiaping is one of the developers of the open source system that I'm going to talk about here. And I also want to acknowledge the Mayo team of software developers. This was quite an effort to build a system that is open source, to release it, and we still have the growing pains of building the community and the governance of the open source system. So I'm going to talk about an open source system that is very specific, and it focuses on mining the clinical narrative part of the electronic medical record. So within the field of computer science, that is artificial intelligence and natural language processing. And probably not very many of you know about the field of natural language processing. Actually, maybe I should do a poll, since everybody seems to be doing polls. So how many of you know about natural language processing in general? Oh, great. Wonderful. And FYI, natural language processing was brilliantly showcased by IBM in the very recent Jeopardy challenge, where the machine won. So it's a wonderful application of natural language processing. However, what I'm going to talk about and what Jiaping is going to demo briefly, actually not that briefly, is a system that's specifically tailored for the clinical narrative. So I'm going to talk about CTEX, the system, the open source system, at a very high level. Then we are going to present one of the core data structures that CTEX builds upon, and that's called the type system, which I believe will empower you to start contributing if you're so interested. And then Jiaping will show you an actual coding example of how easy it is to build annotators within UIMA, which is the Unstructured Information Management Architecture. So just a few definitions to ground us. First, what's information extraction? You have this very loose text, and you want to convert that text to some structured form that you can manipulate. So this is what information extraction is. Information retrieval, on the other hand, is finding the documents that are relevant to your query. So this is the paradigm that Google functions on. Named entity recognition is a subtask within natural language processing of finding relevant mentions of specific semantic types. And the reason named entity recognition is very important is because it's a building block within understanding the semantics of the language. So what we want to do is go beyond what Google does, which is simple keyword searching and pattern matching. Then natural language processing, as a field, is computational methods for text processing based on linguistically sound principles. So we get lots of inspiration from the fields of cognitive science and linguistics, and of course implement them with computer science numerical methods. Clinical NLP is a subfield within the general NLP because the clinical language has lots of peculiarities and characteristics, so you have to have a very focused effort on building a system for mining the clinical narrative. On the other hand, there is a vast body of biomedical literature, and those are the PubMed publications. So the subfield that focuses on mining those records is biomedical NLP. So what is the problem space? It's definitely not the structured information, because those are relational databases or some other structured databases. We all know how to get information from them. It's not the semi-structured information space. It is definitely the unstructured, the textual, the linguistic, the narrative part of the EMR. So here's one example, and it's a very simple example, Linguistics 101. Here's a sentence: I saw the man with a telescope. And linguistic and cognitive science theory argues that this is how we as humans process language. The first step that we do is probably parsing the words within that sentence. The second one is that we abstract to a slightly higher level to attach some grammatical tags to those to those words, and they're called part of speeches. Then we start gathering up the meaning, the semantics of the sentence. So when you first read this sentence, you're thinking, okay, what's the meaning? Is it the man who has the telescope, or is it me who used the telescope to see the man? And the first meaning is represented by this parse. The NP indicates that it was the man who had the telescope, while the second parse indicates that I used the telescope to see the man. So now this is a very difficult problem, and we as humans probably will ask follow-up questions to understand the full semantics of this text. However, machines cannot ask follow-up questions. So the challenge for a machine is how to get to the meaning of sentences like that. So at the very high level, what methods do we use? Some of the tasks are fairly simple, and you can do rule-based approaches ranging from pattern matching or any explicitly written rules. However, other problems, like the semantics, are very complex problems, and you have to combine different techniques, different technologies, and we usually use machine learning, statistical methods for getting to the meaning. So, as I said, I want to distinguish ourselves from what Google does, because we don't do keyword matching. We try to get to the language understanding, because that's very important for mining the clinical narrative and the biomedical literature. So we want to get to attributes of the mentions, like the negation. We want to find relations between the different mentions. So, for example, what medications are used to treat cancer, or what is the location of the cancer. Things like that. Are there any side effects for a medication? And we definitely want to create very sophisticated timelines of the clinical events related to the patient. And you can get to this only through semantic processing and higher level processing of the clinical narrative. So this is pretty much the space that we had to work with. So we set ourselves the task to build a system that at least provides the foundation for building a very complex, sophisticated solution, and that's CTEX. So CTEX was released about a year ago, and at that time Jiaping and I were at the Mayo Clinic. And the goal was to build a system for phenotype extraction, general purpose system that is not tied to any specific use case. So if you want to apply to breast cancer or rheumatoid arthritis or irritable bowel disease or pediatric diseases, the system should be able to work, which is very different from what has been done in the field, which is usually very use case specific applications. Then we wanted to have an expandable and modular system, because we envisioned to add more layers and more modules to that system. So whatever we have has to be expandable. We also set as a goal to use cutting-edge technologies, both from a software engineering point of view and programming software development point of view, and also natural language processing and machine learning point of view. Then another requirement was that we envisioned this system to process millions and millions of documents. So it's not a toy system. It has to be very scalable. And at the Mayo Clinic, it is being used to process over 80 million documents of clinical narrative, which equates to 80 billion words, because we in the natural language processing community measure volume in words. which is significant. So here are some of the technical details. It's open source, and that's the URL. It's a SourceForge project, so you can go, you can download. There is a very active forum. There are lists, support all the typical attributes of an open source project. We also have publications, and I will show you a screenshot of that. The system is built in Java 1.5. It is released within an Apache license. It's not yet an Apache project, although we would love to see it become an Apache project. And actually, probably within the next 3 years, we will be pushing that agenda. The framework, the engineering framework, is IBM's unstructured information management architecture, the so-called UIMA, and it's an Apache project, and UIMA, as I said, was brilliantly showcased in the Jeopardy challenge. So we know that it's scalable, we know that it works. And also, while at the Mayo Clinic, we had a collaboration with Mayo, and I want to give Mayo full credit for pushing IBM to release UIMA as open source. Initially, they were very adverse to that idea. However, with lots of pushing from our end, UIMA is now, or has been, an open source project for a number of years. The methods are natural language processing, and as I said, the application is high throughput system. So what are the core components? And this is a snapshot of the first release. Since September of 2010, we have had a very aggressive release schedule. So every couple of months, we're releasing a new module. The last release was last week, and it was a smoking status classifier. So the classifier goes through all the documents for a given patient and finds the smoking status for a given patient. So if you want to participate in the smart app application, I guess you already have some of the tools to build a smart app on. So the core components, probably I'm going to bore you, but I want to acknowledge this. These are not very parallelizable components. Unfortunately, we cannot use Hadoop to farm out the different processes. We can, however, farm out at the document level. So sentence boundary detection, tokenization, morphological normalization, part-of-speech tagging, shallow parsing, named entity recognition, which I mentioned is very important to start to get to the semantics and finding the clinical events related to the patient. And within the named entity recognition, we use rule-based and machine learning approaches. The types of clinical events that we currently discover are diseases and disorders, signs and symptoms, anatomical sites, procedures, and medications. And I want to underline, I'm not going to enumerate all the standards that we are using, but I want to underline that we adhere to existing standards and conventions within the NLP domain and the healthcare domain. So the obvious standards like SNOMED-CT, RxNorm, HO7, we adhere to all this. Within the general NLP domain, the Penn tree bank conventions, predicate argument structure, everything that is within the domain, we try to stay close to. So there are no idiosyncratic attributes within the system. Here's an example. So if you have a sentence like that, we have a template for the medication, and in this case it will be triggered because there will be a medication mention discovered, and that would be tamoxifen. Then this template will be triggered. That's based on HO7 standards, and then the values that are found for that medication will be populated. And that becomes the structured form of the textual representation. Here's another example, no evidence of cholangiocarcinoma. Cholangiocarcinoma is marked up as a disorder, and there is an associated code, and that's the SNOMED-CT code. the certainty is marked up as 1, meaning that the algorithm is very confident about this object. The context says that it's a current disease. The relatedness of the patient is that it is true, meaning it's related to the patient, and the status is negated, meaning that the patient doesn't have cholangiocarcinoma. So you get all these attributes, you have a template, and then that's then stored in a relational database. We were quite meticulous, and we evaluated every single component of the system, and also we had a number of use cases. So I'm presenting a screenshot of the publication. I want to highlight the result for the named entity recognition part, and that's 0.824. The maximum is 1. So obviously there is a lot of room for improvement. So I would invite the community to start improving what we have so far. So with that, I'm concluding the high-level overview of the system. And now Jiaping is going to talk about core, I guess, software engineering topics like the data structure, and then he's going to show you an example, coding example.
Okay, do you want to answer any questions before I start?
Yeah, do you want to take questions real quick?
Yeah.
Negation.
Yep.
It really works.
Okay, I should.
That's like the mythical problem. That's like the hardest of the
So
problem.
let me show you the result for the negation. An overlapping parser. I know that we had a result for the negation. I believe it was in the 90s. However, MITRE, the company, they are developing a new negation detection algorithm that will be a module within CTEX, and they're going to release that within a couple of months. And I know that it will be an improvement over the current release. Yeah. Oh, and actually Yale released several components within CTEX, and one is negation, improvement of the negation detection. Yeah.
In the examples you were showing, did the parser need to know it was parsing a medication versus a disorder? If you had a longer paragraph with like medications and disorders, would it detect what it was trying to create the structured output for?
So here's how it works. So at the chunker level, you will have the noun phrases and the verb phrases and prepositional phrases identified. So all the noun phrases will become now candidates for named entity mentions. So each noun phrase will then be passed through the algorithm to discover whether it's a relevant clinical named entity mention. And the mention can be a medication, it can be a disease. So in that process of passing the NP, the noun phrase, to the named entity recognition module, it will be tagged for the semantic type. Is that making sense?
Yeah, thank you.
So one of the big core components within UEMA is its type system definition. And you can think of the type system as something like a UML diagram, but without all the methods. So you have to define sort of the classes and their attributes. And we will start with a complete view. Oh, it's not really readable there, but so this is a complete.
It's not supposed to.
Yeah, it's okay. All right. So this is the complete view of all the types that are supported within CTEX, and let's step through each part of it. So the inheritance structure is represented here, but without those arrows in the regular UML diagram. So here you will see uema.tcast.annotation is the kind of the highest level of something that you can represent in CTAKes, and then document ID, segments, that's sentence, base token, new line token. They are they inherit from the annotation class, and it's pretty obvious from the names that this is a segment or a few paragraphs of the document, or a sentence of a document, a base token, it's just something like a word. Then let's step through this. At the highest level, we have a document, which is just, we marked the entire document as this object. And then we assign an ID just to the document. And then we split the documents into several segments. And so the segment, in Mayo Clinic, our documents are in a CDA structure, so there are explicit markers within the document saying which part is a segment or which part is a new segment. But if you don't have those explicit markers, on CTAKes we'll just call the entire document a segment. And then the sentence splitter, the sentence detector, splits the entire chunk of text into sentences. And then the tokenizer splits the sentences into tokens. And then we define a few types of tokens. I think the probably most interesting one are the word tokens. They correlate pretty much to what a dictionary word is, but not exactly the same. I would not go too much deep. Then this lemma is just a normalizer, so it will give you the canonical or dictionary form of a word. Like it will recognize went is the past tense of go. And then context-dependent tokenizer, it will group several base tokens into a more meaningful token. A particular example is a date annotation. So if you have 3/14/2011, you will have 4 or 5 base tokens, but the contents-dependent tokenizer will recognize those 4 or 5 tokens form a date annotation. Then we have the chunk, which is the shallow parser, to recognize adjectival phrase, adverbial phrase, noun phrase, list, etc. Lookup window annotation is more or less an internal structure that defines which chunk of the text to look for potential named entities. And now here, the identified annotation is the core of the named entity recognizer. Named entity, the named entity type has a few attributes here. A type ID, which corresponds to the semantic type of the named entity, the disease, disorder, sign or symptom, anatomical sites, etc. We have confidence here, a segment ID indicating which segment this named entity is in. And then the most interesting part is the ontology concept array. It is an array of UMLS codes that this named entity is supposed to be. So UMLS assigns CUIs to all the source terms. So CTAKes will grab those CUIs and match those in the text, and then assign those CUIs to the named entity that it recognizes. There are 2 additional attributes that got highlighted here is the status, indicating whether it's a current value or a history of. So the text can say the patient has a history of. I don't know a good example of. Oh, whatever. Yeah. So then this status value will get assigned a history value, and then certainty indicates whether this named entity is negated or not, like no evidence of carcinoma. Whatever. Then property is just a bunch of metadata that you can assign to the document or any other attributes. Any question about this part?
So you said in the name entities that you'll map to the UMLS codes and the ontologies, right? And
Yep.
Correct me if I'm wrong, but that's a constantly evolving ontology, right? So how often do you guys keep up with that? Is it a big problem? Do things get redefined? Does that change the way you train and produce mappings?
Currently, it's not a statistical method. So we don't use the original UMLS. We will, but the constant is there, which is subset the UMLS, and then create a database that she takes, understands, and then she will query that database and get the CUI out. So if you want to update to a new version of UMLS, you can just create the database and it should update. This is the UEMA plugin for Eclipse. It just provides a nicer view of this XML file that basically defines what you want to run and what parameters you want to pass to the component. These are the components that Guergana mentioned in her slides. So we start with the simple segment annotator and then segment detector, tokenizer. This is the normalizer, context-dependent tokenizer, part-of-speech tagger, shallow parser. And then this is the actual named entity recognizer. And then we have status negation. And this is another, this is just a preparation step. And then let me give you an example of how it looks. So this is a piece of text, like patient complaint of headache. When you run it, you will get a bunch of output, like the chunk. You have a noun phrase, a verb phrase, a prepositional phrase, and then another noun phrase. You also get tokens. And I think the most interesting one is the named entity. So here you will see the CUI from UMLS, and actually CTEX finds more than one SNOMET code. So it will give you all the SNOMET codes that it finds and the CUIs. And this is the semantic type in UMLS. So you probably don't need all of these information, like the part of speech, the noun phrase, and etc. This is something that you can quickly extract named entities from CTEX. Our code is not actually that simple as the smart got started example, but if you look at the core of this part, it's just you get an iterator of all the named entities. You loop through them, find the ontology, and then just print them out. So let's run something here. So this is the UEMA collection process engine, and it lets you point to a directory of files that are in process and what annotators you want to run, and then just click the button. It should run everything for you and gives you the output. So let's let me overlay this. So I've output so this is the output. The initial file was patient complaint of headache. Here it is. Let's see. This is the original file, patient complaint of headache, and then this is what you get from this code. So this is your named entity, and then this is the code associated with it. If you want more attributes like the negation status or any other attributes, just print them out there. So there is a little bit of learning curve of but that's mostly the UEMA framework. Yeah.
I guess this is more of a practical question, but how does your natural language processing work in realistic terms when the language is not natural? So, for example, here you're missing an indefinite article patient complained of headache.
Yeah.
And a lot of doctors' notes are going to be very unnatural in nature, and so a lot of your language models won't apply. Can you learn the model as you're going, as well as, because you're basically applying a bunch of patterns to match these parts of speech, et cetera, to build the structure? No?
Currently you have to build, the models shipped with CTAKes are built from Wall Street Journal data and clinical data. So it actually can work with those kind of unnatural language, but if your notes are way too special, you have to build your own model and then plug in the model. CTAKes should work with that model.
So we actually developed gold standard corpus of part of speech, sentence boundaries, part of speech, text, chunks, and now we are doing the deep parses and the predicate argument structure and semantic roles. And that corpus is clinical notes. So the models, the statistical models are built off that data. So the models learn to recognize these types of sentences, bare noun phrases, missing verbs, all that kind of truncated prepositional phrases, all that kind of stuff, yeah.
Hello. Do you have some sort of a probabilistic matching so that if you have, say 4 different ways that a sentence can be parsed with different probabilities, different likelihoods, then can you propagate those likelihoods through your entire inference process?
I guess the question is, so for example, for the chunker, if it can be a noun phrase or a verb phrase, something like that.
Exactly.
And then how are the probabilities estimated? So we use maximum entropy. So within maximum entropy, the algorithm discovers the chunk that has the highest probability associated with it based on the training data. So all those probabilities are taken into account, yes.
But you pick the highest likelihood at each step and then pass that on to the next step?
Correct.
Okay.
Yes. So, yeah, I guess you can do very fancy machine learning. You can have different classifiers with different statistical methods, and then you can combine them in some voting mechanism, yes. But we are not doing that right now, yes.
Yeah, I think it's doable. So now our annotators just save the most probable representation in the internal UEMA structure, but you can represent multiple representations with a probability, and then you just write your shallow parser so that it reads all the possible representations and do inferencing on those probabilities and gives probability to its output.
So I believe that's what IBM is doing actually in the Jeopardy. They have very sophisticated ensemble of machine learning methods, and they combine them in a final voting scheme, yes.
The other point I was making was, this is a recording, so. The other point I was kind of inferring was that you can also not make the final decisions until the very end. So you propagate a cluster of hypotheses all the way through, and those at each stage, those hypotheses are then translated into the hypothesis space of the next stage, instead of making a hard decision at each stage. And that actually gives you a much richer result set.
That's a very interesting, idea, yes. But we are not doing that,
Okay.
Definitely, there is a lot to explore. And I think inferencing by itself is a huge problem. But I don't think we are there yet. So we are building additional modules. For those of you who are interested, we are building deep parsing module, dependency parsing, predicate argument structure, all the types of UMLS relations, and also temporal relations. And those are very sophisticated modules. And then once you have the output from these modules, you can start doing very interesting inferencing, for sure. Yeah.
Yeah, I think any for all this time, or I think that's if people want to see more. I mean, just process. It gives a sentence or a paragraph, and it gives you the CUIs that associate with them, and you can extract particular named entities or do whatever query on those named entities. And if people want to see more, I can definitely show. But it's basically.
Let's take one or two more questions.
Sure.
I'd have a very specific use for this kind of technology, and I'm curious if I'm not using SNOMED or another standard system, can I input my own, and can I map abbreviations of concepts that I know my providers to be using to the overall, say, for example, diagnosis ontology?
Yeah, if you have your own list of terms, you can just put it into a specific format, and CTEX should be able to use that as your source, and then give you whatever code you assign to the terms.
And we should mention that CTEX is not released with the dictionaries, and the reason it is not released with the dictionaries is because of the licensing issues of UMLS. However, Jiaping posted a script of how you can create the dictionaries of the UMLS. So CTEX is released with a toy dictionary of about 15 terms, and you can use the format of that toy dictionary to include your terms and just run it with your terms. So if you download CTEX and if you have a clinical note and test it on a clinical note, don't be surprised that it will discover only 10 terms. That's because of the toy dictionary that it's included.
One last question. Have you considered at all using NLP to actually make like triplicate like semantic databases out of that information? So I'm looking to my left and thinking of the Eagle Eye folks here who may or may not be looking to use a tool like CTEX to extract a bunch of coded information and then basically build up, thing, predicate, other thing as a giant triple store.
Yep. And that's where we are going with the temporal relations. However, with the temporal relations, we are at the very beginning. We have a colleague who is taking the output, and she's working with the OWL format and first order predicate logic to then make inferences on the triples. Yeah. So you will have event, and then the temporal relation. And then of that, you can create all kinds of additional logic.
Great. I think we're on to our next speaker, so thank you very much.
Yeah.